Welcome to my talk, The Container on Windows Who Escaped the Silo. In this talk, I'm going to demonstrate how a malicious Windows container can impact the host it is running on. My name is Eran Segal. I've been in the cybersecurity field for over 7 years. Currently, I'm research team lead in Safe Breach Labs. My experience involves vulnerability research on Windows and embedded devices. So I'm going to start with a background of Windows process isolated containers. Then I'll continue to how to gain AntiSystem inside of the container. After I gained AntiSystem, I'll show the method I use in order to find 2 vulnerabilities that can impact the host. After that, I'll show a demo containing chain of vulnerabilities, and we'll finish with a Q&A. So the goal of the research is to find what is the impact of an attacker-crafted Windows container on the host it is running on. I chose this research because containers are everywhere. This attack vector is a real-world one, and reverse engineering Windows kernel is fun. So let's deep dive into Windows containers. Containers are similar to virtual machines. Each container is created from a container image which contains all the dependencies for the container. For example, the application that it will run, the file system, registry, and the configurations of the OS. Container image contains all the dependencies, therefore it's easy to manage and deploy, like VMs. But in Windows, it is possible to deploy the containers via 2 methods, which defines the degree of the isolation: process-isolated containers and Hyper-V isolated containers. Hyper-V isolated containers are very similar to virtual machines. They have their own kernel, and they communicate over the Hyper-V of Windows. The container can't interact directly with the host. It has to go over the Hyper-V interface. Therefore, they are more secure, but it comes with computational overhead. Process-isolated containers are similar to the Linux containers. The entire container runs from the user mode, but process-isolated containers interact directly with the kernel, and they are isolated from the host via multiple aspects. But in order to validate that the container won't be able to impact the host, there are a few mitigations in the kernel that validate that. For example, it prevents loading driver from the container to the host, to the kernel. In this presentation, I'm going to focus only on process-isolated containers. So when we are running a task list inside Windows container, we see lots of system processes which are related to the OS itself. Unlike Linux, which doesn't contain system processes inside the container, these differences between the Windows container and the Linux container are because of the architecture of the kernel itself. Both Linux and Windows containers are running from the user mode only, in order to validate that the container can impact the host. Linux container is monolithic, therefore all its basic functionality is implemented in the kernel itself. Unlike Windows, which some of its functionality is implemented in the user mode, while other is implemented in the kernel. Therefore, Windows containers contain services, system services, such as SVC host. So let's deep dive into how process-isolated containers are implemented. There are 2 parts for Windows containers: the engine, which manages all the containers, for example, Docker container, and the OS part, the Windows part, which is responsible for the isolation, isolating the container from the host. I'm going to focus only on the Windows part. When a new Windows container begins, it creates the environment required for the container, such as object namespace, file system, job object, and creates the processes that are running inside of the container. Windows container isolation is separated into 3 parts: job object, namespaces, and layers. This talk I'm gonna focus on bypassing the kernel isolation of the job object. So let's understand what is a job object. Job objects were created in Windows a long time ago to group processes as a single unit and manage the resources. For example, CPU time, and memory limits, and so on. But in order to support isolation as well, the job object is required to be converted into a silo. Silo provide basic isolation, but it is not enough for containers which require much more. So in order to have all these capabilities, this silo have to be converted into server silo. So any server silo is also a silo. After we converted our silo to server silo, which support redirection of resources, now we can redirect resources, for example, registry, network stack, and object manager, to use the resources from the container image and not from the host. But this isolation is not enough. As I said before, the kernel requires to mitigate dangerous syscalls. For example, a load driver. So if it was possible to load driver directly from the container, it could not be that isolated, and the container could escape. So some validations were added to the kernel and validate that if the context of the thread that did the syscall is inside of the container, it will block the request and won't load the driver, as you can see here in the screenshot. So let's deep dive into this mechanism. So when the kernel needs to detect if the current process is isolated, such as in a container, it checks for server silo in the e-thread or e-process structs, which are the structs in the kernel that represent the threads and processes. The kernel needs to check all the job objects which attach to the e-thread and e-process structs in order to validate that, because it is possible to attach multiple job objects to a single thread or process. Another example of a flow in the kernel which requires to validate if the process that did the syscall is inside of the container or not is process list. In this flow, the kernel just skips the processes that are outside of the container. And because of that, when a process inside of the container does a process list, it gets only the processes which are inside of the container. So after we understood how containers work, let's gain AntiSystem inside of the container. When running docker run command with user flag, we can define the user that the container will start. For example, container user, which is a weak user. I would have expected the container to run as weak user, but as you can see on the slide, some processes inside of the container are running as system. The only process running as a container user is CMD that we started. It means that the container can communicate with processes with system permissions. And more interestingly, these processes are loaded from the container image itself that we can control. So no matter what the user flag was indicated, it means that we can gain system permissions. So let's understand how to use this discovery and gaining real system permissions. In order to craft a container image that will run as system always, we can follow 4 simple steps. First, start a container in our lab with system permissions. And then we will create a service that will run as system, start it, and convert the container into container image that it will be possible to deploy it again. The way I showed you is not the only way. We can gain system permissions via multiple ways, and I'm sure there are even more than the ones that are showed here. Because we control the image, so we can overwrite system32 executables that are loaded from the container startup, use DLL side loading, modify Windows configuration, changing the registry, and even changing the permissions of the container user that we are starting. So we gain system permissions inside the container, but we can't do anything we want on the host because we are still isolated, and we can't do anything we want with this system. So in order to understand how to break the isolation, we need to learn about two past vulnerabilities of container escape. Each vulnerability represents a method for finding a vulnerability in containers. The first method is to look for APIs that Microsoft just forgot to block. Unit 42 found a vulnerability in Object Manager symbolic link that let a process inside of the container access any hard drive on the host, which means that the container can write arbitrary files and control the file system. The second method is to try to bypass Microsoft mitigations. James for sure found a way to bypass the kernel validation of the server silo by creating a new silo object, which is not a server silo. Microsoft added the support for containers after most of the kernel APIs were written. Therefore, I chose to look for this first method, for looking for APIs that Microsoft just forgot to block. In my research, I'll focus on vulnerable syscalls, but there are over 500 syscalls, and each one of them is huge. So I had to find better patterns to look for. So as I said before, it has to be a syscall. And the second check is that there are no validations of isolation. This means that Microsoft possibly forgot to add them. The third one is tricky. Checking administrator privileges. If the syscall requires admin privileges, it means that the impact of the syscall is high, which means that we can impact the host drastically. It can be a major info leak, or it can impact the host in a way that it won't boot again. So I thought about writing a script to validate that, but it was easy to do it manually, so I didn't have to. After I built this recipe, my life became much easier, and I began to find vulnerable syscalls. I did a quick triage, and the first function that took my eye was anti-query system information. This function contains a huge switch case over the enum, which contains about 200 options. It's not possible to reverse it manually. Luckily, I had symbols, so I could choose only the interesting enum values and focus on them. So I wrote a small code that triggered only the interesting ones, and I found an interesting result. So when I called this syscall with the enum value of syshandle information, it returned to me a list of all the handles and the addresses of objects in the kernel itself. All the processes on the host itself, which means that we can see process IDs of other containers and processes that are running on the host. But it is not possible to use these handles or addresses because we can't open process to a process which outside of the container or duplicate a handle of him. So it is a minor info leak. So we can get all the process IDs of all the processes on the host. But I want much more, so I continue to look. Additionally, syscall I found was AntiSystem Debug control. AntiSystem Debug control is similar to the previous one. It also have multiple options depending on the enum value. I saw that this function called multiple interesting functions, such as enable kernel debugger, but all these options were blocked only if the kernel debugger is enabled. Sorry, only if it's disabled. The only two options that on a clean Windows machine will work are dump user mod, which won't give me any actual value because I need an open handle to it, and kernel dump, which definitely will do the work. So in order to do a kernel dump from the container, I need to fill the struct sysdebug live dump control, which contains two important parameters. Handle to a file in the container, it's easy, and flags for dump and page control, which defines how the dump will look like and what it will contain. I took a source code from the internet that triggers the kernel dump. I changed it a bit and managed to call a kernel dump, to do a kernel dump and read it from inside the container. So let's look about what we dumped there and the flags. The flags were undocumented and the ones that I found listed here. The interesting one is dump user space memory and the Hyper-V pages. I attached a VM with a kernel debugger and tried to do the dump with a VM. And it worked. I managed to dump all user mod, Hyper-V, and all the flags that I found. But on a clean Windows machine, all the flags worked except one, dumping the user mod. So if the kernel debugger is enabled, we can dump LDAS, which contains all the processes, all the passwords in Windows. So if we can dump LDAS, we can access it. But on regular machines, kernel debugger is not enabled. So let's understand how to gain passwords using the kernel dump. So there are multiple ways to gain them. The first one is process list. We can access from the kernel dump all the processes and the parameters they can access. We can access the environment variables that are passed through. We can access the arguments. In addition to that, we can read and query all the registry that are loaded on the host itself. And sometimes passwords are stored there as well. And if kernel debugger is enabled, it is possible to gain all the passwords much easier with LDAS. And of course, kernel debugger is not only about passwords. We can see lots of other interesting information. For example, EDRs, detect which one are running from, view event logs, stack traces, kernel memory, and much more. Additional vulnerability I found is related to the UEFI. So in order to understand the impact and how we can use this vulnerability, I give a little bit of a background. When we boot a new Windows PC, it probably will boot in the following sequence. First, the UEFI inits the CPU, loads the UEFI drivers and devices. Then the UEFI reads the NVRAM memory in order to know how to continue the boot. Then the boot sequence passes from the UEFI to the Windows. On the third step, Windows begins the boot sequence. Windows pulls the configuration from BCD, which are stored on the EFI partition, and then it continues the boot until Windows fully loaded. Let's focus on the NVRAM storage. So the NVRAM contains a configuration of the UEFI. These configurations are not stored on the hard disk, but on a chip on the motherboard. This memory is shared between the operating system, Windows, and the UEFI itself. In order to access an NVRAM variable, we need to know its GUID, unique identifier, and its name. Two examples of interesting NVRAM variables are boot and boot order. Boot is a variable that defines for the UEFI how to boot using a specific method. For example, boot from a specific file, boot from hard disk, network, and so on. Boot order defines the order of the boot, whether we are going to define boot from CD first, hard disk first, and so on. The boot variable sometimes linked to a file system, files on the file system. But these files are found in the UEFI partition in FAT32. So the container can't access them, so we can't use it. The UEFI support multiple types and flags. The variables can be permanent or they can be volatile. And it is possible to mark each variable when it is possible to access it. For example, access on boot only, so it is not possible to access him from the Windows part, or is it possible only to access it from the Windows part? After we finished the introduction, let's jump to the group of vulnerable syscalls, which are related to the NVRAM API. The first capability we need is listing NVRAM variables on the host. We do that using the NVRAM variables, which are accessible from the container, from the host itself, without reading them, which leads us to the second syscall. We need a specific NVRAM variable that we already know the GUID and the name from before. Microsoft didn't block this syscall from the container as well. And the last capability we need is writing the NVRAM variables. So now we can read, write, and list all the NVRAM variables that are in the host. So let's understand what we can do with it. After the container is killed and start over, all its storage under some configurations are reverted. NVRAM storage is permanent. So we can use this storage in order to store persistent storage. And this information will be stored between container reboots, host reboots, and because NVRAM variables are stored on the motherboard itself, it can stay even up between formats. Additional impact is that we can communicate between two containers, isolated containers. Both of the containers can communicate with NVRAM storage. So we can read one variable and write it from another, which leads us to a possible exfiltration data between them. But the most interesting impact is triggering permanent denial of service of the host. Because the UEFI parses the NVRAM variable, it is possible to change some of them and make the host unbootable forever. By changing the boot and boot order doesn't prevent the UEFI from booting because because the UEFI have backup configuration which are flashed on the UEFI. Therefore, I have to look for other flows. So another variable found in the NVRAM is HDDP. Writing non-valid value to it will do the job, and it will cause permanent denial of service to the host. This variable is read only on the boot. So after changing this variable, nothing will happen on the host. Only after the host will shut down, and it will shut down as expected, and try to boot up again, it won't be possible to load the Windows again. So it doesn't matter how much restart you try to do for the host, it won't work. But this variable exists only on some UEFIs. on VMware UEFI. If we will run Windows container inside Windows VM, running VMware machine, for example, ES6, VMware Workstation, the UEFI of the Windows VM is the vulnerable component. So when we are writing HTTP variable from the container, it will cause the VMware VM to permanent denial of service. The host of the machine won't be impacted by this. So let's deep dive into the vulnerable component in the UEFI. The UEFI is built from multiple parts. The vulnerable one is BDS driver, which is responsible for selecting which device to boot from. The root cause in the BDS DXC is that it reads the HTTP variable, and because we are overwrite it with invalid value, it jumps to the function assert EFI error, which loops over, which breaks the boot sequence and calls the permanent denial of service because the UEFI now can't continue and load the Windows part. So let's jump to the demo. In this demo, I'll show the privilege escalation that I showed before using a malicious Windows container and how I caused permanent denial of service to a VMware VM. So here I'm going to start a weak Windows container with a malicious container. So as you can see here, the user doesn't have admin privileges, but there is a background service that attached to it that reads the input file and writes the output to the output, and it runs as system. If I'll use this capability in order to overwrite the NVRAM variable HTTP and use the service, you can see in here that it wrote 6 times A to the variable. Then nothing will happen until the restart. So now we'll need to wait for the restart, and it will shut down as expected. Everything will go smooth. But when the UEFI will try to load it again and read this NVRAM variable, it will fail to continue. So as you can see here, VMware VM started, init the settings, and it's stuck on this. It won't continue this step forever. So let's explain how the demo works. So before the demo, I created the backdoor service, which runs a system. And it reads and writes to the input and output files. And when we override the variable HTTP and restart the machine, it triggers the permanent denial of service. It is not easy to mitigate these vulnerabilities without official patch from Microsoft. But there are a few workarounds that we can use in order to validate that we won't be vulnerable to these flaws. The first and easiest way to do is to use Hyper-V isolation and not process-isolated containers. But it will cost us with the performance overhead. Another way is to just trust the container images that you run and only use signed ones. And another solution is to assume that any process and any container that run in Windows is system. So you should define it in the network topology. Container image scanning used in order to ensure that there are no privilege escalation or malicious content exists in the image. I tested my container against container image scanning, which didn't detect the privilege escalation. But only after I really dug into their website, I discovered that they don't officially support it, but they do show that the image is clean. Sadly, I could not put my hands on a container image scanning product that supports Windows containers. Regarding the vendor responses, the privilege escalation, Microsoft said that because only administrators can start the containers, there is no privilege escalation here. And regarding the kernel dump, they said that it is not a vulnerability because we need system permissions inside of the container. But they do plan to fix it in the future. Regarding the environment variable attack, which we can read and write environment variables from inside of the container, they defined it as moderate denial of service. But it is outside of the scope of Windows Security Update, and they do plan to fix it. And regarding the last one, the VMware UEFI variable, HDDP, VMware treats it as functional issue because it impacts only the VM itself. And it requires admin privileges inside of them. But they do plan to fix it. I uploaded all the tools and code that I use, how to do a privilege escalation using a malicious container image, how to do kernel dump and the modifications that I did there, and a manual for how to cause permanent denial of service like I showed here in there. I would like to thank Mickey for helping me reversing the VMware UEFI. And I would like to credit multiple other researchers that I based my research on top of them. Thank you for joining. Moving to the Q&A session.